Okay, yes, feel free to take your seat. All right, mic is working, right? I think so. Yep, good. Thanks, and welcome, and thank you very much for joining us today. It's pretty hard to compete on popularity against the Warriors, so I understand. I hope for a little more attendance, but I know I could never compete with them. And telling you the truth, if I were not at this event, I would also be watching. All right. This was unfortunately set up before, so I was kind of almost praying for them to finish up last Friday instead of today. And I hope they finish up today, by the way. All right. So my name is Akara, and I work for PayPal. I'm in the infrastructure team called GPF. We are working on an open source project called squbs. Today, I'm not going to talk too much about squbs in general, but we are just pulling out some areas of squbs. One area that is quite popular is the orchestration DSL. Next time, I might talk about some other areas. Okay, so we'll probably have a series of these going. And I think this one is a standalone module or a piece that you can just use in any project that is Akara based, right? So going over the agenda a little bit, I'll take one slide to talk about squbs and what's there, right? I'll talk about the use case for orchestration. And in my experience, most of the applications that we end up writing are some sort of orchestration applications, right? We try to break it down and say, how did we do this in the past when we had only synchronous systems? And how are we doing it now, where we have asynchronous systems like Akara? And we found a way to describe the dependencies of the orchestration in ADSL. I think one of the areas that gets skipped a lot in product talks or even DSL talks is how do you handle errors? How do you handle timeouts? And I think that's a very big thing here, right? So I'll explicitly talk about it, talk a bit about integrations, and then finish up. And hopefully we'll be out of here by about 8. But feel free to ask questions if it's short questions. If there are long discussions, I would appreciate if we keep it to the back, to the end of the talk. All right? So what is squbs? Squbs is basically, let me just give you some background. When we started the project, Akara Spray were libraries, and it's very hard for us to say, okay, let's go build your application, and 5 people will build their applications differently. So we created a way, it started with a way to bootstrap and hook Akara into operations, into logging, monitoring in a standard way, right? But then it has grown. And we wanted people to easily adopt that, so we started working a lot more on the programming patterns. And what we are talking about today is one of the programming patterns, which is orchestration, right? So what is orchestration? If you write some service that takes a request, could be of any form, right? And then you say, go and check authentication. Go and check authorization. Go and look up the content. Go and call this service and update the database here and there. You can see that you are talking to very many resources. And in many cases, these resources can be accessed concurrently instead of one by one, which makes your latency very high. Okay? So in this picture, we are just showing that you have this orchestrator that talks to many of these resources, synchronously or asynchronously in request-response mode, or, let me see whether this is working. I'm not sure. So, oh, that's going forward, I'm sorry. So, or in the case of a triangle, which we use a lot in Akara, where we say, we send a request to one worker, it forwards, or does some of the processing, forwards the request to the next worker, which then makes the response. That is also pretty common, right? So this is what we call orchestration. There is a lot of other orchestration, like orchestrating in the cloud, which is a different thing, where you try to provision for boxes and virtual machines and so forth. That's not what we are talking about today, right? So, talking a little bit about synchronous orchestration. So in synchronous orchestration, you basically come in and you say, I need to do 5 things. So I dispatch my 5 things to different threads. These threads call services that are blocking. So these threads again get blocked, right? And it is prone, if you have a burst of requests coming in, your thread pool grows like crazy if you open it up for growing. There's also other issues with interlocking between tasks that are in the thread pool. So with asynchronous systems, we use a message-oriented way that is non-blocking to allow for maximum parallelization without really overusing the resources of the system. And I'm sorry for people that have used TopCat. We are using TopCat and sync servlets as scapegoats. TopCat now has async servlets, by the way, but this is how it used to be done in the past, and how a lot of the world's code still looks like TopCat and sync servlets. But TopCat has done a great task for our communities, for open source, so there is not, I'm not saying TopCat is bad, okay? I'm just using a use case as an example. So let's take a look at how this would look like on TopCat. And this is even using NIO. So we have got an accepted thread, normally, that basically sits on a select loop. Once a request comes in, it basically goes through the connector, creates vowels as you want to, okay, as you have defined, calls the servlet. If you are a JAX-RS service, calls JAX-RS, okay, and JAX-RS again calls your worker logic. Now, you duplicate that. You say a second request comes in, the first request is not done. A second thread is being pulled from the thread pool and doing the same thing, right? If you have 4 threads and 4 requests, that's going to be done, right? So we are talking about n concurrent requests and n concurrent threads in this model. So if you have a thread pool of 50 threads, you cannot go beyond 50 connections concurrently. Now, in service calls, let's say these threads have to make database calls and service calls. Let's, in this case, show you service calls. So the worker logic calls a service client and says, go grab me some resource, go grab me some information from another service, and you sit there blocked and waiting for that other service. So that thread is doing nothing. It's using up memory and doing nothing in return. And the scheduler still has to go through that thread and figure out which threads are ready to deal with, or to come back and get working again. So you do that for every one of them, every thread is blocked. That's it, right? So that's basically not a good use of your resources. That has been one of the big bottlenecks of the service architecture so far. Now, let's take that example and move it into something we have built in the past called service orchestration that then creates another thread pool called the orchestration thread pool. Usually, the orchestration thread pool is much, much bigger than the request thread pool, the TopCat thread pool, right? So let's say the first thread there wants to say, I orchestrate and I want to make 4 service calls. What it does is it creates 4 tasks, okay? Each of them sitting on one of the threads in this orchestration thread pool. I'm showing 4 to 4, but actually orchestration is usually much bigger. So while a sync servlet is waiting for orchestration, it by itself is blocked. And then each of these tasks, let's say they all make service calls outside, they call a service client and go out and get blocked, right? So now you are saying that for each one request thread, you have got itself plus 4 request threads, in this case, blocked. So that's 5 for each. And if you duplicate it out to 4 threads, 4 requests, that would be 5 times 4, which is 20 threads. And in general, we are talking about a thread pool of 50, 100 dependent, right? So that's kind of where our resources are getting used, and threads are not cheap. So we got to be careful in using those. In summary, all we are doing is holding threads. It's being blocked from doing any useful processing, okay? And then it needs a different module to do this service call separately. That's called the orchestrator. Now, as you grow in the number of primary thread pools or TopCat thread pools, you grow exponentially, actually, in the number of orchestration threads, to the point that we easily saw 300, 400, in some extreme cases, 1,000, 2,000 threads being used in a system, and that's not very useful. That the system is not dealing with it very well. The context switching, the scanning that has to be done by the operating system, which thread is ready to run, is going to be pretty high. So one day we looked at something called Akara. And Akara is an async message passing middleware. Who in this room is already using Akara? I've got about 30%, I would say. 30% of people here. So Akara is an actor-based middleware. Let me just elaborate a little bit more, since we have only about 30% of the people using it. Okay. An actor, you can think of an actor like you and me, right? We all have memories of what we are doing, and we context switch to do something, and then context switch out of it. An actor behaves in the same way. It holds the state. You remember what it's doing, but it doesn't hold threads. Okay? So it only holds threads when a message comes in and say, now handle this message. Then it gets scheduled on a thread, right? That achieves a system that has got very, very low thread count. And in addition to that, it has got some mechanisms to keep your systems fairly fault-tolerant. That's resilience and supervision. I'm not going to dive into the detail of that. There's a lot of documentation and talks about supervision already. So let's just focus on the low thread count and low context switch. Let's see how it works. For people that have seen this slide before, I apologize for reusing it, but that's one of my favorite slides. So what happens is you have got an actor with a mailbox that sits outside of any thread, just in memory. Okay? The overhead of an actor is very small. We are talking about 512 bytes or something like that per actor. Right? Now, an actor is not active until it receives a message in its mailbox. Right? Then the actor will get scheduled on one of the threads. It doesn't have to be the first one, could be any of those, right? Akara has got this notion of dispatcher, which is basically a thread pool, but a little more than a thread pool. Okay, so normally the dispatcher threads are 1 to 2 per core, which means that on a 8-core system you might have 16 of these, okay, or 8 of these, depending on how optimized your code is. And that actor will then start to process the messages. It tries, based on the scheduling model, it tries. Unix is a time-sharing system. So a time-shared system, there's no guarantee that you will hold on and not get context switched out. But because you have low workload, low number of threads, the chances of not getting context switched out is very, very low, right? So it tries to run everything to completion. And on top of that, if you have got multiple of these messages, right? Multiple of these messages will be pushed in for the actor to process in one scheduling cycle, which makes it very, very efficient, right? Sure. It's a standard Akara configuration, right? I don't remember that off the top of my head right now. Anybody remember here? What's the thread per CPU configuration in Akara? It's in the application.conf. Very easy to find, right? Okay. So now, let's look at the asynchronous orchestration model. Okay. So in the async model, similar to the previous picture that we have shown, a task is represented by actors or services. Usually I've got an actor that fronts the service, right? Tasks are dependent on each other's only by the input and output. So if they don't need an input from another task. That task can run in parallel, or is allowed to run in parallel. Okay? If it requires an input, it has got this dependency chain or dependency graph, right? And you declare that dependency in the DSL. Okay? The task can run as soon as the inputs are available. But they may not run at that point. Let's say you have got a thread pool of 4 threads. In the case of 4 threads, if your 4 threads are processing, it might not run right away. So that also sends a message saying async is not exactly equal to parallel. It just says it can run. It doesn't say it will run. Okay? If you have got something else that hogs the thread pool, that task will never get run. So be careful about this. Having talked about the concepts, I would say let's go into code, right? So the rest of the talk is mainly code. So before we start, let's look at your library dependencies. For orchestration to happen, you only need one dependency. That's aux.squbs and squbs pattern. The current version is 0.80. If you want to go for 0.81 snapshot, that's available on Sonatype. There is no change though. We haven't updated the orchestration module. So 0.80 is the best you can get right now. So once you have that done, you go and start writing your code. And writing your code, you can see that this is just a standard actor, right? In this case, to avoid other complexities, I'm just passing in all the other actors that you have to orchestrate with. There are many other ways you can look up the actors. Squbs even provides an actor lookup module or registry module that we can use for that. But here is a simple way to do it. Whoever calls it passes in, or it might go through a dispatcher that knows all the other actors that you have to talk to, right? One thing that I didn't mention so far is the orchestrator actor is a one single use actor, which means that this instance of the actor is used for one request coming in, pushing out messages to n other actors or other services, getting the responses back in, and then process that response, return a result to the original requester, and this actor is done. So you have to terminate this actor, right? This is to avoid complexities of handling concurrent multiple requests in one actor. And it's very cheap to create an actor, so let's create one for this.
Question.
Yes?
How does other languages like Python code or Java choose similar code? For example, in OpenStack, similar requirements.
Yes.
And the underlying architecture, same hardware architecture.
Okay.
So basically,
So the question was, how would we achieve the same effect in Python or in Java? I know that Python does a lot of async I/O, but I'm not a Python user by myself, so I'm not qualified to comment about Python. But even even though I'm showing Scala code here, we have Java support for this module, right? So in Java, you would the DSL is not as nice as this, but you would represent the same thing using a chain of completion stages in Java 8. Are you familiar with Java 8 completable futures and completion stages? So if you go to the documentation, and that's all in Squbs, there is a link for orchestration. There is a Java version as well as a Scala version.
So once compiled to assembly, the assembly will be the same?
Yes.
So Java, Scala, so the only benefits is less code?
It's less code, it's more idiomatic code, right? And also the conventions in Scala forces you to do better things, right? It basically says, for instance, immutability. In Java, you have to enforce it by hand. And it's very hard to enforce it because people write Java beans left and right. But in Scala, you write case classes which are immutable by default, right? Yes?
So if classically imperative languages, you start locking out a lot of mutexes, then you lose a lot of efficiency.
Yes, exactly. So you shouldn't do that. Even in Java code, when I work with people, customers or users that say, I want to use Java, I would work with them very closely to keep everything as immutable as possible. And when I see any context, any locking that happens, I would say, no, this is not acceptable. You won't gain anything if you do so. So this is a lock-free. You shouldn't see any synchronized block, and even, I would say, no volatile, right? So no locking in this architecture. So let me talk about this code a little bit. So in Akara, there is a module or a pattern in Akara contrib called aggregator that provides you this expect once. So orchestrator is an aggregator, and it's an advanced version of aggregator. So you can think of expect once as a receive block in Akara. Actually, the type of it is actor receive, right? And it says the first thing is I want to take this input, and I want to call a function called orchestrate. That's just the way that we name it, so that everyone looks the same way, thinks the same way. And when you orchestrate, what you in effect do is that the sender, which is a call, will get frozen into that requester field up here. I don't think no, this is not a laser pointer. So the requester field holds the original requester, or this sender in the first case. And inside the orchestrate block, or the function, is where most of your orchestration logic goes, right? So this is almost boilerplate. I'm thinking of doing something better than this. If you have some ideas, let me know, reach out, okay? So now the sample. This is my sample where you have got an input, right? A request coming in. The data from the request has to pass to two tasks, task 1 and task 2, which can take the input directly. And then task 3, that is bound to task 1 and task 2, takes the output of task 1 and task 2. Task 4, that takes the output of task 2 alone. And task 5, that takes the output of task 3 and task 4 as an input. The output of task 5 is the output that you can respond back to the requester, right? So now a little bit on the orchestration DSL. The orchestration DSL here has got, the first part is you want to do task 1. So we define an orchestration function called do task 1, takes input and creates a output of task 1, what I append f to is a future, okay? Task 1 future. Do task 2 takes the the input and has a task 2 output future. That is normal. There's no magic in that part. The magic really starts at the third line, which is task 3. So with task 3, I only have a future. I don't know when that future will complete. So I say, I take the future of task 1 and task 2 and pipe the output whenever it's complete to do task 3. Okay? Similarly, for task 4, there's only one input. So if you have 3 input, you just put 3 input in parentheses. 1 input, you don't need parentheses, right? And you pipe it to the orchestration function, do task 3, do task 4, and do task 5. At the end of do task 5, you have got the task 5 output, which then gets resolved, saying whenever task 5 is resolved, which means the future is done, right? Then I want to send, so the bang is a send or tell, send the result back to the original requester and then stop myself. Context.stopSelf is stopping myself in Akara. Okay, so pretty simple. So this actually reflects the graph that you are seeing pretty directly, all right? So what are the characteristics? Of course, we talked about single-use actor already. Yes? Oh, sorry. Absolutely.
So task 3 will wait for the output from both task 1 and task 3?
That's correct. So if you think about it being a callback, saying that if task 1 and task 2 are done, both, then do task 3 will get invoked. Right? Think about it that way. So this is very declarative. Yes?
And can you declaratively specify that task 1 and task 2 should run on 2 different things? Or is it by...
It's asynchronous. So we don't even specify. it takes the default dispatcher and runs it there. Or if it's a service call, it will call out asynchronously and only come back when the response comes back, right? Yes?
So is the scheduler aware of the granularity of those tasks?
No, it is not. So each of these tasks, think about it as a separate actor. And the scheduler is aware of the actor itself, right?
So the learning time of different tasks may be radically different.
Yes, yes. Could be totally different. You have no control. It's asynchronous. Yes?
Haven't you considered some libraries for applicative functors in order to write it just as a single for loop with all the compositions?
Mm-hmm.
Haven't you considered like Squbs, applicative functors, or?
I looked at that early on. This is not new, but they might have advanced quite a lot.
Yeah, because
right.
you could unify it just to one for comprehension then.
Oh, actually the first version of this was a single for comprehension. The problem with a single for comprehension is if you call the functions inside the...
To launch, but
yeah.
I believe that if you are using applicative functors, it's not an issue.
Really?
I think so.
Let me take a look at that. Right, I looked at it early on, but it might have changed a bit over the years. Yeah. Yep.
Okay,
So what it does actually internally in those piping, it's basically doing a set of flat maps, right? Yes.
why we cannot put all of this task 1 and 2, task 5 into that same for comprehension?
Oh, yes, that's the first iteration that we made. Basically, if you make a function call inside a for comprehension, the resolution of the function call is actually synchronous. We want that to be totally asynchronous. That's one of the reasons. But let me take a look at Squbs applicative functors a little bit more, right?
Or synchronous implementation, so implementation of applicative
Yeah,
functors.
and actually the logic behind the arrow or the pipe is fairly simple. It is basically a for comprehension without the final map.
Yeah, but you're having this dichotomy of initial declarations and then your loop, and probably you could put this contact.stop to the parent method, to the method in the superclass. I mean, you could implement some basic method and then to call your implementation in that and then call context.stop.
Let me just go through the rest of the slides.
Yeah.
We can have this discussion at the end because I'm not sure whether that's the right thing to do. If you still think after you look at the slides, I'm willing, absolutely happy to listen to that, right? So again, it's a single use actor, right? The state is kept. So these look exactly like Scala futures, but we built a separate set of promise and futures called O promise and O futures. And this is O for orchestration. The reason for that is Scala futures run their callbacks on a different thread. And that could conflict or cause concurrency with the actor itself, right? Because you are trying to modify an actor state from a thread outside the actor. And so we wanted to have a model that looks much more like the synchronous callbacks, synchronous by the way, callbacks of the, say, completable future in Java 8, okay? So the O future is basically exactly the future, except for that it is fulfilled by a message coming in to the actor, or a response message, and that response message, the thread that causes that response message, causes the chain of actions, chain of callbacks to happen. So it will never run outside the scope of the actor. So what we call a close over in functional programming will never ever cause any concurrency issue with the actor itself, right? That's the only reason for that, okay? And then, of course, at the end, you resolve the final result from the O futures, the final O futures that you have, okay? Whatever needs to go into the result. Let's define an orchestration function, how it looks like. An orchestration function has the signature of a function that takes any input of any type. I'm not sure whether they resolve the 22 in a tuple, but for sure up to 22, okay, inputs, and returns an O future of the output type, right? So in this case, we refer to these as do task 1, do task 2. In practice, we don't call it do task 1, do task 2, but in this case, we do. Okay, just to show you clearly what it's doing. And usually, this makes service calls that return a future or calls another actor, right? We have got, I'll show you both versions. One is to use ask. The other one is to use tell. The ask version is usually easier to write. The tell version with an expect is actually a little harder to write, but performs better. Uses less memory based on what we have done. That's why we'll talk about that. So let's take a look at the first case, right? So this one is do task 1 with a single input and an O future of task 1 output. Of course, with ask, you always have to give it an implicit timeout. If you are not familiar with Scala and not familiar with implicits, an implicit val, think about it as an environment setting, if you are familiar to shell or other scripting programming language. Perl also has environments. So, but it works by type. So it only takes one type of one instance of timeout in that case, right? Otherwise, if there's a conflict, the compiler will barf and say, oh, I found more than one of these in scope. I don't know which one to use. If you don't provide it, the compiler will also barf. Then you basically say, I want to call my actor, say call it task 1 actor, ask with that input, and map the response to an task 1 output. Now, if you do that, the ask is actually returning you a future, right? It's not returning you an O future. How does this code work? It uses one nice little feature in Scala called implicit conversion. And it says, okay, inside, and that's basically in the orchestrator trait, right? Saying that if you return with a future, I know how to convert a future to an O future. So you just return a future, and it will take care of it. So the second version, in this case, I'm just showing, for example, do task 3, which has 2 inputs, right? So you take the input, not a future. Input 2 is not a future. In this case, you want to create an O promise. Use an O promise. It's faster. Trust me. Okay? Then you basically tell the actor, saying, I want to give you an input, and derive that input from the 2 function inputs that you have. Send it to the task 3 actor, and say, I'm expecting a task 3 output, task 3 exception, right? Again, expect once is part of the aggregator. It's not a DSL, aggregator pattern inside of Akara contrib, all right? Then you say, okay, what should I do if I have an error and if it succeeds? So if it succeeds, you get an output, you do a promise.success O. If you get an exception, you do a promise.failure E. And again, this expect once block is run asynchronously. So if you try to jump with your debugger, it will jump over this block and go into the promise.future line, the last line. Because that part, that block, will only be called once the response comes back. All right? So at the end, you say, I return a future. What's the difference between a future and a promise? Why don't you want to return a promise? A promise is mutable. And you don't want to expose mutable state out of your function, right? So you can complete a promise. You can change a promise. You cannot change the future. Think about it that way. So you always want to return a future, not the promise itself. So promise.future just does that. So next is and actually to your point about when or where to stop the actor. In some cases, you want to always stop it. Some cases, you don't want to stop it, right? And don't look at the gray out part up there. Look at the second part here. So we had the orchestration DSL up there. Down here is, now I want to make sure, what is reactive systems about? Reactive systems are about being able to respond in a timely manner, no matter what that response might be. The response might be that I didn't get anything from downstream. So I'm giving you a response that I didn't get anything from downstream. But if I say, I want to respond to you by 100 milliseconds, I want to respond to you by 100 milliseconds. Okay? Instead of sitting in a stack-based system, sitting there waiting forever and not coming back, and then it times out downstream, might be 5 seconds down the road, right? So here I say, if I don't get a response, do something. And this do something can be much more complex. This is a very simple example. In this case, it says, schedule to send myself a timeout after 100 milliseconds. So if the actor has done all the orchestration and the output is already done before 100 milliseconds, what will happen is the timeout message will just arrive in the dead mailbox, which will never be processed because the actor would have been completed, right? But if it comes down to timeout first, it means that the other things are not done. So in that case, I want to send a timeout to the requester. In real code, a little too much to put into a slide here, I would check all my futures and say, which futures are not done? List them out for debugging, log it, saying these things. These services, service A, service B, came back, C didn't come back, and log it, and then also send back a response saying, I'm sorry, I don't have all the results for you. In some cases, you can even say, I have preliminary results. We have got those use cases too. And I don't have the final results. I can only give you the preliminary results, right? And after that, I want to stop too. What's next? Again, ignore the gray part. Look at the white part there. What if we say some of the orchestration tasks come back in failure, right? So you would basically say on failure, do something, okay? If it's a failure of an expected exception, you might do certain things. If otherwise, you might do something else. So on failure is also taking a partial function, which allows you to list all the cases that you want to handle and can handle them differently. In some cases, you want to stop yourself. In some cases, you might say, I might want to call another service instead. Let's say I call service A. Service A is not responding in time. I want to call service B, for instance. Or service A errors out. I want to call service B. That is definitely possible. A little more error handling. So this is just nothing beyond Scala futures, where you can use a for yield to say, if task 1 is successful and task 4 failed, I want to do certain things. Or if task 3 is failing, I want to recover. Task 3 is not critical. I don't want to stop my actor for that. If task 3 is not coming back with an answer, I want you to take this default output, or I want to call task 4, recover with calling task 4 instead. So we can do all that with the great composition of the exception cases of futures, right? So I'll stop the difficult parts right here and just jump right into kind of summarizing this. All right, if there's any comments, questions, please feel free to raise your hands. Yes?
I have a basic question is, if any fancy feature or demanding feature cannot be accomplished at assembly level, what kind of fancy language or fancy language features you can accomplish which cannot be accomplished at assembly level?
There's nothing.
An example, we can launch 1,000 virtual server or servers, physical servers, bare metal servers, like with one command using Scala or whatever language. But actually, they are either pseudo-parallel. Can they be true 100% parallel?
Well,
which means, it's not a pseudo.
No. If you talk about this, right? Basically, this depends on your I/O library. We all use async I/O libraries here. So usually we only have, let's say, 4 threads. You cannot go more than a parallelism of 4 on this system, right? But with async I/O, basically at least it lines up saying thread 1 makes service call, thread 2 makes service call, thread 3 makes service call, and then you can go up to thread 1, go around thread 4, then back to thread 1.
In a queue. So
Right.
suppose there are 1,000
Yep.
threads that can be launched simultaneously, then we can truly accomplish.
Okay, one more point on that. All the threads that you launch boil down to the CPU pipeline underneath.
Yes.
So threads are an illusion in that sense, right? That's why we try to configure it to be equal to number of CPU pipelines. So threads also get context switched in and out. They are not running in parallel. That's why the parallelism of this is 4. But since you are doing async I/O, you can launch all the requests for 1,000 requests on 4 threads in very small amount of time. It's not parallel. The parallelism is still 4, but then once it's launched out, it might be parallel somewhere else across 1,000 boxes, and when it comes back, it might not come back at the same time, but there are 4, and everything gets queued up to be handled by these 4 threads, right? So it is as close as you can get to parallel, but essentially, we don't have more resources than the number of CPU pipelines.
Sufficient CPUs.
Yes. Yes.
Do that, right?
Yes. If you have sufficient CPUs, you can do that.
Too expensive.
Exactly. Right? So let's summarize that. And what we get out of this is a high-performance async orchestration. Okay. The key part, the key takeaway of this is one of the very few architectures, Akara in general, and message passing systems that could give you a relatively timely response. When I say schedule something to come back in 100 milliseconds, there is really still no guarantee that it's going to be exactly 100 milliseconds, but it is as close as possible, unless you go to a real-time system, which is a totally different ballgame. I'm not going to talk about that, right? But it schedules that into your mailbox, and then if while the 100 millisecond mark comes back in, you are processing the last response from your orchestration tasks, then your actor would have terminated before this timeout message has arrived, right? So there might be a case where a response comes back when you say 100 milliseconds, say 105. But it's not going to be far off. It's not going to be like I say 100 and it will be 1,000 generally, right? So it keeps the SLA pretty well. And the error handling, of course, I have been working with people that actually use this, and they have Java code that have try, do something, catch, and then in the catch, they try to recover from that, try, do something else, and catch, and have a nested try block in that manner, which is actually, even they told me, that's their biggest source of bugs in their system. And by using a composition of features, it allows you to handle each of these use cases in a very streamlined manner, right? The code complexity has been reduced dramatically with this. So how do you use it? You have all this. Actually, this is just a slide in case you don't know, so I'll just go through it. Very commonly, we use Spray, or we use Akara HTTP, and a request comes in, it dispatches the message to the orchestrator. That's one of the most simple use cases. We do have Akara Streams use cases. Akara Streams achieves certain way of orchestration already, but it's not as flexible. It's basically a branch in the pipeline right? So it is common to make a call. Let's say you need certain orchestration to be done as part of a stream stage. You basically call map async or map async unordered, depending on your use case, and call and ask inside that and start an orchestration from there. For each message, you start a different orchestration, right? If you are in part of any actor, you can, of course, do an ask or a tell. Or the last case is when we have very complex orchestrations where you don't want to contain everything in one orchestrator. You can do a star model where basically one of the orchestration tasks actually maps to another orchestrator that does 5 other things, right? So you have got orchestrator that orchestrates into many other orchestrators going forward, all right? So those are the normal use cases. I didn't draw a picture of that, but if you have got 1,000-line orchestrator, you don't want to do that. You want to break it down into manageable, smaller orchestrator. I think we have a use case like that, that basically, in order to get one data point for the main orchestrator, it has to call another 5 services. That's where we say, okay, let's break that out into a separate orchestrator. Okay? So, now, having talked about squbs and wanted to leave some time for discussion, I'll just try to end this and say what else about squbs. I started in the beginning, squbs is about, it started with trying to bootstrap Akara Spray and make it consistent across multiple deployments so that when you have an organization like PayPal that has got thousands of these services or software components, that each of the Akara ones will look and feel the same to operations, to logging, to monitoring. You know, so in that way, it just walks like a duck and quacks like a duck and would fit into the operational environment. And squbs is basically extensible to fit into your environment. The PayPal parts have been abstracted out to keep inside PayPal, right? We have an extension model where you can stick in extensions, especially for logging, for knowing when a request comes in. Some people have the requirement to say, I have to log every request, and I have to log every request going out of it, saying I'm making service calls, and I have to know this is the incoming call resulting in outgoing call A, B, and C. That has to be all logged in the system. So how do you make that happen without telling every user of Akara to implement their own logging, which might not be consistent? So those are the use cases for standardized plugins or extension models. There is a module, actually I have to credit one of you in this room to, that made this happen, actually, data center aware clustering, right? So Akara clusters are great, and we found it very useful. I think they fixed the bootstrap issue, but it doesn't work very well when we have a cluster that needs to span multiple data centers and know that you are talking about a node that sits in a different data center versus one in the same data center and has got different latency characteristics, right? So data center aware clustering provides that. There's a zookeeper-based coordinator in there. There are other pieces like the registry. I briefly talked about that. So if you don't want to pass all the orchestration targets in, what do you do? So you can use similar to a service resolution or service lookup. You can have an actor registry that provides an actor lookup API saying, give me somebody who can give me a payment record, right, for instance. So with that actor registry, you can look up by name, you can look up by request type, response type. Monitoring. Monitoring has been there from the very beginning. You just drop it in. Unlike the orchestrator, which you can use as a library without using the rest of squbs, the monitoring goes with squbs, unfortunately, with the bootstrapping. It plugs in and says, I want to know what each actor is doing, how big their mailbox is, right? And monitoring actually exposes all the information through JMX So with that, we also provide a little console. It's a read-only console, which exposes, and JMX, by the way, is not very good at remoting. JMX remoting is very expensive. So it takes JMX local and exposes JMX as pretty-printed JSON, right? So you can actually use a JavaScript module, something like that, to ping all your Akara nodes and then obtain the state. Or you can also watch it by hand, basically, because it's pretty-printed JSON, it's very easy to read. And this is one of the patterns that we are talking about, one of the older patterns that we have. We have got many more. So if you look into Akara patterns, there are quite a few of those. All right? So with that, I think we kind of gave you an overview and dove into the orchestration. Any questions? Of course, now is the time.
Last question. How was the multi-data center clustering problem solved?
Solved, all right.
Due to latency variation?
No, it's not.
It's not.
It's,
the namespace? Or
okay. So the answer is it's pluggable. Okay. So, based on our experience, in our case, we have got a different set of IP addresses in different data centers. So for instance, we have a module that says recognize that this group of the IP addresses are in a different data center. You can overwrite the same module and say, I want to use latency as a decider. It's up to you how you want to decide it.
So you classify based on IP address?
That's what we have right now. But it's a pluggable module that you say, I don't want to classify by IP address. I want to classify by other attributes to recognize. I can probe and ping those systems and say, if your latency is, let's say, inside data center, latency should be below 5 milliseconds. Outside the data center, it might be 20 milliseconds. And if you go into that range, you recognize that that link is.
The real question is, due to asynchronous nature, is that true that the real-time constraint cannot guarantee with that kind of feature, Akara? Because it's asynchronous, so real-time constraint can never be guaranteed.
It's true, all right? It is true. Let me just be very clear, but I would not conclude that without an asynchronous architecture like this, you can guarantee it. Unless
Except a different language, true real-time language.
if you have a real-time language on a real-time operating system. That's the only way you can guarantee. So let's say you want to control an ABS brake or the adjustment system of a fighter jet, right? That keeps the fighter jet flying steady. Those are hard real-time systems. And you would never use such a system to build something like that. In terms of timeliness, it's much better than everything else, so. Right? All right, yes?
I think if I'm not mistaken, payment services are in the REST services are SOAP services, so I'm curious how this thing is coming into
Okay. This squbs, I'm not sure how much I can say that, but I can only say that the payment service is not on squbs, right? Let's say it this way. I don't think I can talk much more which ones are not. Okay, but the payment API that you are using, accessing via a REST API, that is not a squbs service. Yes?
You touched upon the latency a bit. How is synchronous versus the non-synchronous guarantee the latency?
None of that actually totally guarantees the latency. None of that. This is much closer. In a synchronous orchestration use case that we talked about earlier, the only way you can guarantee latency is to schedule an interrupt back into your thread, which is a very dirty way of exiting your thread, right? But that has been done. All right? With this, at least, you are not hocking on the stack. You basically say, if I say 100 milliseconds, trust me, it's going to be within 105, right? In that way.
Based on how you schedule.
Yes, and how quick the latency inside the Akara system is very low.
Assuming that your number of threads are less in asynchronous.
Yes.
Versus more in the.
Right. And when you get the thread attention, here you are getting it for good, basically, because there are so few threads that you are not getting context switched out in the middle. In a large thread system like what we had before, 500 threads on 2 processors, there's no guarantee at all.
For the same throughput, would it be different? Latencies would be different for the same throughput?
An async system, we achieved many, many times better throughput than yes.
I'm talking about the latencies.
Yes.
In terms of latency, for the same latencies,
yes.
The latency be better than on asynchronous than asynchronous?
Okay. So this is a long debate that we could have about the latency being more or less, or the accuracy of the latency. So async systems like Akara are very much more based on queues. And how do you control the latency of the queue? That's one argument, right? But at least you can control the latency once you get attention of the thread. Once it's scheduled, basically your thread is not doing anything else but this. In a current synchronous system with large number of threads, how can you guarantee that you will get scheduled on the CPU? So it's different guarantees, right? So if you ask me, I would say experience tells me that this is much more timely, but to prove that in theory is going to be very difficult. And it depends on the test cases, but in general, we see much better responsiveness, especially at high loads, especially when you are running 90% CPU. The system still gives you timeliness. And that's kind of the promise of the reactive manifesto, right?
That's the way it's built, right? Synchronous versus asynchronous. But are there better checks and bounds on synchronous versus asynchronous? Here?
None of them have it. Yep. This has got, at least it says, at 100 milliseconds, which could be 101 millisecond, because if you know the contract of thread.sleep, for instance, or wake up, it says that if you say sleep for 10 milliseconds, the guarantee is it will sleep no less than 10 milliseconds. It will never say that it will come up at 10 milliseconds, right?
The problem, the question goes back to how do you make a trade-off between latency and throughput?
In here, there is a couple of parameters, I would say, in this system, right? So the throughput, there's a parameter called throughput. The throughput tells you how many messages an active instance can process in one scheduling cycle. If you increase the throughput, of course, the CPU is going to be bound to that actor and others will have more latency. So you have to tune this to, yes, there's a trade-off, right?
No free lunch.
No, there is no free lunch. And we are not saying that there is free lunch, at least your life is much better this way. That's all I can tell. Any other questions? All right, I'm still around. Thank you very much for coming.